Okay, so I had to find this chart, but now we can start. Uh, so, today I want to tell more about the wave equation, namely about boundary conditions for the wave equation. Uh, so, hello, did you say?
There is some kind of echo. I don't know why it is. Maybe there are two mic on.
Hmm?
So
No, what the problem? Let me check. Mm, mm, I don't know. There is just one microphone.
maybe
Hmm?
no, maybe no, it's okay. I don't know why there was a problem before.
Hmm.
So you can start teaching it. If
Hmm.
I will have problem, then I will let.
Mm-hmm. Okay. Before we were studying the string which was infinite. So this is x, and this is u. So it's what u of x. But now we can uh, uh, add some boundary. Let us start with the problem with just one boundary on the left. Namely, let us say, so there are at least two possible options. One option is to say that this end of string is fixed. So it's one option, which means that u of so it is x, this is u of t0 equals to 0. Another option is to say that this end of string is free, which means technically it means that we uh, put that we put here some, for example, rod, put some massless ring which can move along it without friction, and say that string is attached to this ring. So, since it can move freely, it means that vertical projection of the force of tension should be zero. Or in other words, this string should be perpendicular to this vertical axis. Which means this condition that x derivative of u at this point is 0. Uh, uh, so there are basically these two initial conditions, but in principle we can consider something more exotic. For example, we can say that there is some string attached to this ring, and to try draw something like this. This ring and the spring attached here. And in this case, there will be some angle, and the force acting on this ring will consist of two parts. One is the vertical projection of this tension force. So it's 3, which equals to so F result in U equals to T times, let us call this angle minus alpha, T times um, sine of alpha, plus elastic force, which is proportional to the to this distance, which is u of 0 minus with some elasticity coefficient. And it should equal to 0 because uh, this ring is massless, so its acceleration, so um, like m a equals to f. Second Newton's law says that f should be 0. So if you now say that alpha is small, as previous approximations, then it gives us t times ux of t0 minus k of u of t0 equals to 0. So this generalized boundary condition, and we see that these two are particular limits of this when t goes to infinity or k goes to infinity. Or better maybe to think about the ratio. This is called Dirichlet. And this is called a Neumann boundary condition. So, are there any questions about this? Okay, so it's a formulation of the problem. So we will not study this case because it is usually hard computation. We will study this first two. So now the question is how to solve such problems. So first, let us formulate it. Since now our U is defined, since now this string lives in the right half axis, this equation should be defined only on R plus. So we have this equation utt minus uxx equals to 0 for t greater or equal than 0, x also greater or equal than 0. And we also have initial conditions and boundary conditions. So u of 0x equals u0 of x, ut of 0x equals to u1 of x, and also some condition on the left boundary, namely u of Uh, Let us start with this first case. So here u of t uh, 0 equals to 0. Uh, we see that if we want this initial condition to be consistent with the boundary condition, we should also ask that u0 of 0 is 0, but it is some in essential restriction, in a sense it's easy to achieve. Yeah, just remember about this. Mm. But so, now the question is how to solve this equation. Uh, so uh, And the idea is the following. Since our equation lives on the half axis, we can continue it to the whole axis by choosing these initial conditions in some appropriate way. Uh, so it's called a method of reflections, and it has also some other generalizations. So if we have some function which is 0 at 0, it is natural to assume that it actually comes from some function which was antisymmetric with respect to x2 minus x. So it was some odd function originally. Uh, so idea is the following. We need to try to construct uh, uh, u of t and x such that u of t and x, u of t minus x equals to minus u of t and x. But it's actually easy to do because um, our U is originally so it's first requirement. Second requirement is that for x greater than 0, U of t and x equals to well coincides with solution of this equation. Mm. But it's a very easy problem because suppose that our u of tx solved the equation. Mm. So the question to the audience, who can explain why? What precise property of this equation is important? Hmm? Suppose that we have some function u of t and x which solves the wave equation. Now the question, instead of this, we consider function u of t minus x and try to substitute it into the same equation. Will it solve it? And if yes, why? Yes. Mm-hmm. Yes. Yes, I understand. So if we compute d2 over d2 over I can write it here d2 over dx squared of u t and x it is the same as d2 over d minus x squared of u of t and x. Maybe let us write here minus x. So if if this solved this solved the wave equation in the variable minus x. So we had inequality d2 over dt squared minus d2 over d minus x squared u of t minus x equals to 0. So d2 over dt squared minus d2 over dx squared u of t minus x is 0. So that's all. Uh, if we now want to solve to solve mm, so let me think. Mm. If you now want to write some solution of this equation, which is defined on the whole line and is 0 at 0, we can just do the following. So on the right half line, write just u of t and x, which we have. Um, because we are solving this equation on the half line. And here it is by definition that, well, can I write in the same picture? Can I draw the same picture? So it looks similar at least. So here u of t and x is by definition u of t minus x. Oh, sorry. Minus u of t minus x. This u, maybe let us say that we are defining some u tilde of t and x, which is defined on the whole line. Uh, so here we define it this way. This u tilde acts on r greater equal 0 times r. Mm, so maybe let us denote the variables t greater or equal than 0 rx. So this function is defined on the whole line. And now it solves the wave equation. by construction, more or less. And initial conditions for this function can also be obtained from this continuation to the negative half line. So u tilde of tx um, should equal of 0x should equal to u0 of 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 x. It's for x greater or equal than 0. 0 of 0 x should equal to minus u0 of minus x for x less or equal than 0. Mm. And the same for its derivative. So we just take these initial conditions and solve the equation. And mm, if you draw, so are there any questions about this? Mm. And now we can draw some pictures as before with the same initial condition. So suppose that we put this triangle at some point, for example, here. Then, so I don't want to draw all this evolution of this triangle into two triangles, but uh, just draw a result of this evolution. So we will have this triangle somewhere here, this triangle somewhere here. Maybe it's better to draw this one twice higher. So it separates into the two triangles. But the question is what happens next? Because until this moment, it's not important that our string is fixed at 0. But when we reach 0, something starts to happen. And to understand what precisely, we need to remember about this mirror image of this U, and this mirror image looks like this. So there is this triangle here, and it evolves in the same way, because this solution is antisymmetric. So we have this triangle and another copy here. So and so we know that this goes in this direction, this goes in this direction, this goes right, and this goes left. So they will pass through 0, and probably I don't know if I want to draw this process. Oh, probably it's possible to draw So let us draw it. Mm, so at some moment we will have picture like this, when this triangle already moved to the negative half line, and this triangle moved to the positive half line. So it will mean that until this point we will have on the same slope, and after this point it becomes twice more steep, and goes to 0, because we know that this function is antisymmetric, and in particular it's 0 and 0. So we continue this linear function like this. So there will be this this interaction between these two triangles, and there is also this one here, and this image here. And after they go through each other, we will see on this picture. So this is somewhere uh, further to the right. And this moves completely through 0. Uh, Here it's an image, and here is the image of on that one. So after this process ends, we see the result. So we don't see what's happening on the imaginary, on the negative ray, because it is just a formal continuation of our solution. But we see what's happening here. We have uh, this triangle, and we have an inversion of this triangle. So it's a kind of a result of a reflection from this fixed left end of a string. So it basically reverses in the shape of a wave which tries to go through this boundary. Right? It's a little bit similar to a reflection of a ball from some ball, that it reverses its velocity. So, are there any questions about this? Yes, of course. Yes. Yes. But well, I can write it everywhere. In principle, it's possible to draw such plots using colors, or using 3D plots. In this case, you will see trajectories of these waves that propagate through string, but uh, I don't know. For me, it's easier to imagine it as a sequence of pictures. But by the way, are you using any software that can plot some functions, like Mathematica or something like this? Uh, So, so you can take some solutions and play with them. Mhm. So, are there any questions about this? Uh, so let us then go further. So there is, of course, a natural generalization of this picture for the case of free boundary. So in this case, we just change the definition of this continuation. Let us define u tilde of t and x uh, as u of t and x for x positive, and u of t and x with the same sign for x negative, plus u of t uh, mm, minus x for x less or equal than 0. So it means that these images will not be reversed, and this reflection will look like this. So we will have this triangle moving left, uh, this moving right, and at the end it will just exchange. So if you don't look at the left half line, it will look like this. That the triangle moves to 0, reflects from 0, and then moves right, but without this inversion. And so this process of reflection will look like this. So I can add another picture here. It will look like mm, well, the sum of two such functions will be this function. So do this way and then goes back. So are there any questions about this? Okay, let us study another problem. Here we solved this equation with boundary with time independent boundary conditions. But what if we try to study a time dependent case? Uh, namely, what happens if we ask u of t and x be some function, let us call it ul of t. And there are also these initial conditions. Well, I'll not write them. The question is what to do in this case. And uh, uh, if you want to study it, we can actually separate this problem for anything we solved before, because this equation is linear, and so we can solve separately problems with trivial initial conditions and problems with trivial boundary conditions. So. Uh, So yes, I suppose that we want to solve the equation uh, uh, well, it is the wave equation for t greater or equal than 0, x greater or equal than 0, and there are initial conditions uh, u of uh, u of 0 x equals u 0 of x u of ut of 0x equals u equals to u1 of x u of t0 equals to u l of t. Mm. Uh, let us solve the following auxiliary uh, auxiliary problems. Like, so this equation is always the same. Then initial conditions u of 0x. Let us denote this u1 of 0x equals to u0 of x, u1 of 0 ut of 0 and x equals 0, u of t u1 of t 0 equals to 0. So here equation is the same. So these three problems um, have two two zeros for two initial boundary conditions and some function just for one of them. And if we now solve these three problems, then we can just write that mm, u of t and x, which we want to find, equals to u1 of t and x plus u2 of t and x plus u3 of t and x. So is it clear why this gives us a solution to the original problem? Hmm? Sorry. T0, of course. Sorry. Mhm. Yeah. And in principle, we already saw this phenomenon even for this first two problems. We saw that a solution with a linear combination of something that depends only on u0 and something that depends only on u1. So it's clear because the equation is linear. So, other question? So, and it also applies to the situation when we take linear combinations of initial conditions. So a solution of this equation will be linear in the initial conditions. So if you say that u0 is some combination of such function, then u will be a combination of solutions with such initial conditions. We can write more generally. So if u0 of x equals to u0 1 of x plus u0 2 of x, then u of t and x will be a combination of two solutions. Like this. So all this means that if you want to solve this general problem, and you already know how to solve the problem with initial conditions and with zero boundary conditions, like these two problems, you only need to solve the problem with zero initial conditions and with some nontrivial boundary condition. And so, so we have a problem. Utt minus uxx equals to 0, u of 0x equals to 0, as well as its derivative, and u of t0 equals to u L of t. And this holds for t greater or equal than 0 and x greater or equal than 0. So can anyone try to guess what to guess how the solution can look like? There is a reminder that if there's some function solve this equation, then it can be represented as u of t and x equals to f plus of x plus t plus f minus of x minus t. So we see that there is something that should satisfy all this for t greater or equal than 0 and x greater or equal than 0. So who can try to guess? Maybe it's better to write even t minus x like this. Maybe f g. Hmm?
The question is, what is the solution by fixing the position?
Oh, no. What do you mean?
So you have u t0 equals to u and t.
Yes. Mm.
So here you have fixed position.
Oh, it is some law which describes the motion of the left end of the string. Like we move it forcefully according to this function ul of t.
Is equal to minus g.
Uh, well, why do we need to do this?
T equal to 0 is
Yeah.
equal to 0.
Uh,
We have that f plus g is
yes, yes. If you say like this, then okay, we have this condition, of course. Hmm.
the f of x and g minus
Well, it's yes. Sorry, f of x, and it's for x greater or equal than 0, because we don't have we don't know anything about negative x. So it's for x greater or equal than 0. Mm. And but we have another condition, right?
u and t.
Uh, oh, we also have this condition for derivative, right?
Okay.
Uh,
So
but actually, wait, let me think. So uh, this condition says what? That so if you take x derivative, it's the same as to take so here it's the same as x derivative, and here it's x derivative with minus sign. So mm, mm, so d over dx uh, g of mm, uh, minus d of minus x plus f of x equals to 0 for x greater or equal than 0, right? Mm. So we can say that if there are some appropriate boundary or initial conditions, or we just go to t equals to minus infinity, we can say that it's not constant, it is just 0. Can, mm, in any case, these functions are defined up to shifting by some constants with opposite signs. So we can say that this is equivalent to g of minus x plus uh, f of x uh, equals to 0. Uh, so uh, so we have these two conditions. And what do they say about g of minus x and f of x? Hmm? Hmm? What precisely? This derivative. In x, because originally it was derivative in t, but I noticed that d over dt in g of t minus x equals to minus d in dx of g of t minus x, right? Uh, okay, what is the consequence of these two equations? Hmm? Uh, well, we should be a bit careful. We see that f of x for x greater, so f of x equals to 0 for x greater or equal than 0, right? And g of x is, so what can we say about g of x? Oh, so it also equals to 0, but hmm? Hmm. Okay, so yeah, there are these conditions, um, and uh, now let us see what it means. We have this combination of two functions, and in principle we obtained some restriction on these functions only on the half lines. But do we actually care about the values of this function f of x plus t for the negative values? Does it affect? Yes, it's true. But hmm? Yes. Hmm? So yes, it's defined for positive t and x, and so we don't care about this. So without generality, we can just say that f of x is 0. And now what? Mm. Only. Yes. And the next question is, what is so this disappears, and now the only question is, who is G? How to find it? So we already used the initial conditions, and we only need to solve the boundary condition. Yes, UL of x, but maybe it's better to say g of t equals to UL of t. So, well, in this so uh, this g of x, uh, yeah, well, or maybe well, it's UL of x. Yes, it's a solution, uh, and solution of this problem is. Mm, hmm? But it's kind of down variable. You can put any letter here. It's just a statement that two functions are equal as a functions of x. We could write here, I don't know, some Cyrillic letter or something like this. So, hmm? Mm, so, so if you substitute x equals to 0, we get a g of t equals to a ul of t. So we can write here t or any other letter. So it means that functions should equal for any argument. Okay, so u of t and x equals to u l of t minus x. And in principle, we could get this solution from the very beginning because the picture is very similar. It is similar to this reflection method. And so we just draw this profile of UL of UL of minus x uh, on the negative half line, which is invisible for us. And then start the evolution, and this profile UL starts moving into the positive half line, producing precisely the dependence of u of 0 as we are asked. It will be UL of t. So, so it has a very simple explanation. So are there any questions about this? Ah, so uh, let's then go further. So this problems with a exact with simple exact solutions for this equation are almost over. There will be one other problem which has almost the same simple solution. It will be the problem with some right hand side. It corresponds to some force which is applied to the string, and it depends on both coordinate and time. Uh, so this problem will have some solution similar to solution of this initial value problem, but we will discuss it later because we need to know some other concepts. Mm. But now I want to switch to a more complicated version of this boundary of this boundary problems, namely to the case where we have two boundaries. Uh, so namely, uh, we again can have different boundary conditions, but let us study for simplicity the case where they are zero. So u of t and 0 equals to uh, u of t and some L equal to 0. So it is a string uh, fixed at the 2 points, 0 and L. And it vibrates in some way. So it's so finally it is the problem which appears in the real life, and the problem about some guitar string or string in some other instrument. Uh, and also the same happens to acoustical problems because all the instruments have some characters of finite size. Some ends are open, some ends are closed, but they are always limited in space. So such problems appear in most of the practical applications, but they are complicated. They are more complicated than this infinite or semi-infinite problems. So, so So in principle, if you want to write some solution which is valid for some finite time, we can try to use this reflection method because we know what happens at each end. So we can draw these pictures. We can also draw some infinite continuation of this string in both directions with inverted or non-inverted boundary conditions. But if you want to use it, so it will work fine if you want to compute the solution for some finite time. Um, but if you want to find it for any time, we will need to sum the infinite number of these images, and it becomes not very practical. And in this case, there are different methods which also have generalizations to more complicated equations, for which we cannot, for example, write this solutions in so simple form. And this and this methods involve such keywords as separation of variables, uh, mm, Fourier transform, normal modes. So idea is the following. We have our equation. And so now let us try not to find some general solution or anything of this kind, but by the way, people on Zoom disconnected. So we can try not to solve the general equation, but to find some solutions of it. So, uh, uh, namely, what do we have? We have some operator, d over dt squared minus dt over dx squared acting on u equals to 0. And we want to use eigenfunction of these two terms in the sum. Uh, so this is the idea. Uh, and um, since these two operators commute, we can diagonalize them simultaneously. We can have a basis of functions which are eigenfunctions to both of them. Uh, and so, so this remark that d over dt squared uh, commutes with d over dx squared. So 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 let us find uh, let us find some function which is a eigenfunction for d over dt squared and d over dx squared at the same time. So who knows how to solve such equations? Let us add some letters lambda t, lambda x, lambda t, lambda x. Hmm?
Maybe if we have periodic and boundary condition, I think that it could be sinus, cosinus regular and sinus regular.
Yes, but let us. No, so I also to say that periodic boundary conditions are also allowed. We can say that this function is periodic, but in this case it has zero boundary conditions, and we also want these functions to satisfy these boundary conditions of t0 equals to 0 and phi lambda t lambda x of 0 of tl equals to 0. So just to restrict the number of them. But the idea is correct. So if we have this boundary conditions, what can be the solutions? Could you say it again? You said about sines, cosines.
So I think P equal to, okay, so function of P and X is equal to sinus function
Hmm?
of frequency multiplied by
Mm.
P
Mm-hmm.
plus or minus, no, in the
Ah.
same argument of
Mm-hmm.
plus or minus another constant that can be
Some k.
multiplied exactly k multiplied by x
Mm-hmm.
plus p
Phi is
plus
alpha.
arbitrary
Mm-hmm. Mm-hmm.
exactly.
Yes. Uh, it's oh, it's actually generic solution, I think. Yeah, but for this practical purposes, it will be more convenient to write products of sines and cosines. Yeah, because we can write it as a sine cosine and so on. So. Mm.
You say that we use only sine because we have the alpha parameter.
Alpha parameter and plus minus here. It holds for any alpha, so we can expand it as sine of this cosine of alpha plus cosine of alpha sine of this, and coefficients in front of alpha and in front of cosine and sine will be independent, and then we can do the same with this plus or minus functions. Uh, and uh, by the way, what are the eigenvalues of this function? So what is the lambda t and lambda x?
The square square.
Oh, minus only, because when we differentiate, we have one minus in some place. So lambda t equals to minus omega squared, lambda x equals to minus k squared. Oh, by the way, I wanted to ask, what is your name?
My name,
Mm-hmm.
Riccardo.
Ah, mm, ah, eh, yes, you already told. I forgot. Sorry.
Sorry?
You already told this. I forgot.
Ah, okay.
Sorry. No, I'll try to learn. Mm. Yeah, so in general, there are such eigenfunctions, and so we can write them in some uh, in some more convenient way, uh, uh, and sounds convenient for our purposes. Mm. And by the way, if we now act with this difference of operators on this function, it's clear that we will get the difference of uh, lambda t and lambda x. D squared over dt squared minus d over dx squared acting on this phi lambda t lambda x will equal to um, k squared minus omega squared phi lambda t lambda x, because it solves this maybe let us write lambda t minus lambda x, because it solves this two equations. And if we want to use such functions to write some solutions of this wave equation, we of course need to choose lambda t and lambda x equal. So let us introduce the new functions which will be called kind of sine for function uh, of k and x. It will be a sine of kt times sine of kx, and cosine function. Oh, sine of kx.
So
Hmm?
this is another kind of solution for
Uh, Yes, it's just some linear combination of such functions um, with equal eigenvalues for both parts of this operator.
Okay, so if I take superposition of Ps and Pc,
Yes.
then I get that I solve the equation.
Yes, and you can also take a combination with arbitrary case. So, because it solves this equation for any k. And we can also solve this boundary condition because here we choose sine functions in x that automatically vanish at 0. So phi k both cosine and sine of t0 equal to 0. And we also need to satisfy another condition that phi sine or cosine k of t l equals to 0. And the question to everyone. So what does this condition say about k?
The question is, what is the condition in K such that the boundary condition is satisfied?
Yes.
Maybe K depends on primal numbers.
Which?
2 by n with n
Hmm?
no, divided by L
Mm-hmm.
and n in n
Mm. Or natural number. So I would write just greater or equal than 0. Mm. For positive integer. Oh, well, it's almost true, but the question is, if I put here just pi n, will it be fine or not? Because sine of pi, it is what? So, so, sine of pi is in this, it's also 0. Right? So sine of 0 is 0, sine of pi is 0, sine of 2 pi is also 0. So we can write like this. Right? And in particular, for k equals 1, this like for k equals 1, this function will look like this. So it is uh, it will be a sine of pi x over L, and this will be x, L 0. It will be this function, or kn, n equals to 1, n equals to 2. It will be this function, and so on, right? So, there is this condition if you want to satisfy initial conditions. So, so we know that if we want to satisfy both equation and boundary conditions, we can take appropriate case and then take arbitrary linear combination of this phis. So u of t and x will be the sum over n, some an maybe sine of pi t over L plus bn sine of pi t over L times a sine of pi x over L. So it is a solution for any A's and B's. Though the requirement is that this series, so if you take the infinite number of these A's and B's, this series should converge. Mm. 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 So, and concerning this keywords, what was happening here is a separation of variables. These guys are called normal modes, and this series, which is written here, is actually Fourier transform of something. But we'll talk about this a little bit later. Mm. Oh, but for now, the practical application of this formula is the following. So if you have some initial condition which is written by someone to simplify your life, so this initial condition can be some linear combination of such as sine functions. So if you see something like this, you can just write a finite number of terms in this series, and it will be a solution of this equation. So if you want to satisfy the initial conditions, then we can also write that u of 0 and x equals to sum over n bn sine of pi x over L, and u of 0 and t, or ut of 0 and x is sum over oh, I missed n everywhere. Sorry, pi n t, pi n t, pi n x. Okay, it will be sum of an pi n over L sine of pi n x x over L. So if initial conditions have such forms with a finite number of non-zero A's and B's, we can just write them and solve this equation. So it looks like a union of dynamical systems for each of these modes. And we can see it in a kind of more transparent way by uh, performing this transformation with only x dependence. So, uh, so if you see this equation, uh, so if you see some one-dimensional equation like second derivative of something plus something equals to zero, in principle we don't need to do such tricks to solve it. It's already solvable. So to simplify it, we can just perform such transformation with x dependence. So we can um, say that u of t and x is sum of some coefficients cn of t times sine of pi n x over L. And if we act with this differential operator, then sine of pi n x will give just some numbers. So dt squared minus dx squared acting on u of t and x equals to sum of cn primes of t plus pi n over L squared cn of t times sine of pi n x over L. And so and if you want it to be zero, then all the terms should be zero. So this string with a fixed boundary condition, at least for such ansatz for solution, because we don't know yet that it is the general solution. So it can be represented as a combination of independent oscillators with different frequencies. So is it clear analogy or not? Hmm?
Is there any mistake in the expression of u0x? So the coefficients bn and an.
Yes, there is a mistake. I missed the two coefficient. Thank you. So yes, it is bn. It is an. It is bn. Yes. Mm, no, no, probably it's fine, right? Mm. So
So, and the other approach, do you use the series expansion of the coefficient?
um, oh, and not yet. In this approach, we need to solve this equation. But it is so it's two solutions of this sine and cosine. Mm. So it is a finite dimensional equation. So this expansion contains only two terms. I just wanted to show this phenomenon that this mechanical system written in the correct variables becomes a collection of non-interacting systems. That each normal mode evolves on its own. So, mm, so it's I wanted to show it not only at the level of solution, but also at the level of equations of motion. Mm, And uh, and uh, also, we can notice another thing that since these are non-interacting oscillators, then we have some infinite number of conserved quantities. So the consequence of this formula is that sum of sum of Cn prime of t that no for any of them Cn prime of t squared plus this pi n over L squared Cn of t squared, what is denoted En. So d En in dt is 0. So, hmm? So is it clear why it is true? Hmm? Well, let us check. So, um, so suppose that it is satisfied and try to differentiate. So it will give 2 times Cn prime of t. And here we will have hmm? Where?
Okay, to the power of 2 or not? Is there
Yes, thank you. Mhm. So is it clear? So okay, right? So and it is 0. So they are actually conserved. And mm, and it's some remarkable property of the system, because if you take some a random mechanical system with some linear interactions, then the only conserved quantity is usually the full energy and maybe some other integral of motions, uh, not too many of them. In the evolution of the system usually fills the whole surface of constant energy. But here we have this separation between different modes, um, and uh, it means that we have an infinite number of this conserved quantities. And so it's not only energy, the full energy, but also the energy of each mode of this string. So, uh, are there any questions? So, so until now it was just some class of solutions of this equation, but I want to explain that actually any solution can be written in this way. In a sense, any function of x with these boundary conditions. So, are there any questions about this? So, um, uh, so the next topic will be the Fourier transform, but maybe let us make some small break. Let us make some small break before the next topic, maybe for 10 minutes, and later.